use at each stage, so you can keep doing a union bound across buckets and so on. And in log m steps, you're done. And the main tool we needed was this lemma that if variables have small total variance, k-wise independence is actually good enough to get the product of expectation of the product correct, right? Okay, so now in the case of Nissan's generator, going from rectangles to general branching programs was, the same idea just worked. And, it would be nice to ask if, we should ask whether this works for general branching programs. I don't see it working as is. But instead, I'll tell you something else that this works for. That's life.
Like if it doesn't work?
No.
Doesn't know how to prove it.
Yeah. Okay. I'll tell you one more generator which does something more intelligent than this one. That one I genuinely don't know. That if I had to give you a candidate, it would be the generator I'm about to present. Okay, read one CNF. What is this? It's, we're back in the domain of very limited classes of functions. It's a CNF, okay, where the variables, each of these clauses are on disjoint variables. Why am I talking about this class? Well, mainly because Amir said that I should. So, Also, it is computed by a width 3 branching program, but the variables need to appear in the right order. If the variables come in the same order that they are in each clause, then you can compute it by width 3. If the variables come in any crazy order, it's not clear that you can even do this using small width, right? Okay. So the best PRGs for general CNFs, not width 2, they require seed length something like log squared in every relevant parameter. And as I mentioned, the reason you might want to get this exponent below 2 is that this is one avenue towards better lower bounds for depth 3 AC0. It's something which has been open for a long time. It's not clear that there's any reason why it should be very hard to go from root n to n to the 3/4. Certainly parity doesn't work, that's clear. Okay. So why is this true? I think somebody asked this question, so let me just tell you. You don't even need a pseudo-random generator. Even suppose you had a hitting set generator with the following guarantee. You can hit every DNF of size less than, say, 2 to the root n, or make it n to the 0.51, let's say. And density, this should be a greater than. Density at least 2 to the minus root n, right? Now suppose I got the exponent here below 2. Then I would have a non-trivial generator for this setting, because log squared of this would be still something whose support is 2 to the little o of n. It would be a generator with a very small support. Okay. Now I claim that a depth 3 AC0 circuit is going to have a hard time identifying the support of this function. In fact, it will be a little more convenient to work with the complement. So why is that? Let's consider a depth 3 AC0 circuit which has an OR gate at the top, and then you just have DNFs here, right? So this is an OR gate. It could have fan in something like 2 to the root n. Each of these is just a DNF. Okay. CNF, same thing, yeah. Okay. So the goal of this function is to accept G bar. So it rejects everything in G and it accepts everything in its complement. Now the complement of G is a pretty large set. It's almost everything, right? So one of these DNFs has reasonable density. It's accepting a 1 over 2 to the root n fraction of the whole space. Well, but that one is also not too large. It's of size at most 2 to the root n. But then this is hit by the generator G. So it accepts something from G. So the whole circuit accepts something from G, so it can't be computing G bar. So it's a very simple reduction. Even getting a hitting set below log squared n, you're doing something interesting. Okay. Well, and once you have a pseudo-random generator for rectangles, read one CNFs is pretty much, it's not very hard to go to read one CNFs because these things are very similar. If I have a formula with m clauses, I'll assume that each clause is of width log m. Okay, so you can get rid of this assumption very easily. And now you see that it's very similar to rectangles because you want your assignment to hit the satisfying assignments for each Cj. Each Cj is a disjunction. if it's a disjunction on log m variables, that means there are m possible assignments, all but one of them is good. And you just want the cross product of this set, right? So it's very much like a combinatorial rectangle. The only difference is that I don't know the boundaries, So imagine that there's some CNF. I tell you the width is at most log m. I don't quite know what the bins are. The first step in my rectangles generator is to sample rootm things from the first bin. What does bin mean here? If I knew what the first clause was, maybe I could do something, but I don't really know, right? Okay, so you just wing it. You just say that, okay, for each variable with probability half, I'll decide whether or not to set it. If I decide to set it, I'll set it to a random value. And then I'll use something like an epsilon bias set or log m wise, almost log m wise independence, okay? And this basically has the desired effect because sure, I don't know exactly which variables participate in clause 1, but I'm pretty sure that when I do this, I'll kind of set half of them, right? And then I'm setting these randomly. So it's kind of like I'm sampling a random subset of size roughly root m from the satisfying assignments. I don't have, pairwise independence maybe, but you can hope that things look, at least, from a very high level, it seems like you're doing the right thing, right? And okay, now you're using something like log m wise independence. So now your clause width you don't know what's happening to the clause width because you don't know where your clauses are. But you can imagine that as you go on, the width of the clause is shrinking by half at each step. Now, if my clauses are of width something like log m over 100, and I keep hitting it with, say, log m wise independence, then I get 100 wise independence across the clauses. And then when the clause width shrinks by half, the level of independence also doubles. So it's kind of doing all the right things that you want. And finally, we proved that it works. Okay, so it's, this machinery we've set up about random variables, the product of expectations, it's very powerful, and you can just apply it here. Now, you have to be a bit more careful to argue that this process does terminate in log m steps, because previously the alphabet was just going from m, root m, so on and so forth. Here again, it's not quite clear that it's doing that, but you can argue that, in log m steps, you'll be done. Okay. So this gives you a generator with essentially the same parameter for read1 CNFs. Does this work for general CNFs? Maybe it could. I see no strong reason to believe that it doesn't. I see no reason to believe that it does either. But, and in fact, maybe little later on, what is the hard function here? That seems like the first question to ask. And I think the hard function underlying this is the following. Take an epsilon bias set where epsilon is very small, something like 2 to the minus n over 100. Okay. Now, epsilon bias sets alone are not hard for depth 3 AC0 because, as Shrikant told me, every mod 3 is a small bias set and it has AC0 depth 3 circuits of 2 to the root n. But now you do this one more step of take a ball around each point of radius something like n over 10. Okay. So you should really think of this as epsilon bias with a little noise. That's the distribution. That seems to be the hard distribution that underlies this generator. Because if you think about what's going on here, I'm not going to make this formal, but if you think about what this generator does, it very much mimics this distribution. All right. So let's go back to this template, which I'm going to generalize a little more now. So we said, yeah, Amir? Yeah, because, so what should be the analog in the branching program world, right? So the alphabet is basically the strings of length log m roughly. And yeah, I guess. Sorry?
I'm willing to pay polylog in randomness, but the unknown order, that's what.
Oh. Maybe there are many issues, but the one thing I see is that in how many rectangles do you need to argue about, right? So in Nissan's thing, it was very simple. He was just going to shrink n down to n over 2. He needed to argue about poly n rectangles. In our case, we are doing the shrinkage not on the dimension, but on the alphabet size, kind of, right? And then, so what this roughly seems to be saying is that, okay, so from this layer, instead of these m possible strings, I'll maybe pairwise independently sample a subset of size root m, and then try and use limited independence across the layers. Okay, it's a fine generator, but how do you argue that this preserves the acceptance probability of this branching program? I don't know how to do it. You're not talking about 2 layers now, so it seems like you need to talk about a lot of rectangles, exponentially many, and clearly union bound is not going to work there. I mean, maybe that's not a satisfactory answer, but the obvious thing doesn't work, right? All right, so let's keep going. And actually maybe that's in order to do arbitrary branching programs, you need to do things like half spaces, right? Our favorite class in the last few years or so. And even for that, I'm not sure that the generator as it exists would really work. So it seems like maybe you genuinely need to do something more than that, okay? So actually I'm going to talk about Fourier shapes, which are some kind of generalization of half spaces. They are a generalization of pretty much everything we've talked about in today's talk, and of a lot of the questions you've been asking about things like, let's get the distribution right when you're hashing balls into bins and so on. So what is a Fourier shape? Well, you've never heard of this class before simply because it's a class we made up very recently. Again, you have n bins, each has balls. Now, previously the balls had 2 colors. Now think of it as the balls get a color which comes from the unit complex disk. Okay, so each ball has a complex number of norm at most 1 associated with it, and across different bins they could be using different palettes. They don't need to use similar colors. They can take whatever colors they want from the unit complex disk. Okay, now here's the function. It's going to be a function which gives you values in the unit complex disk also. You just take the product of the colors that you get from each of these bins, right? So if you want to think of each complex number as, a vector in the unit disk, then, you're kind of mixing the colors together when you multiply them. So, okay. Now we want a small family of strings in m to the n. So this class of functions, I'm going to call them as Fourier shapes. I want a small class of strings, a small set of strings in m to the n that fools all these Fourier shapes in expectation. There's a subtlety here, which it's worth spending a few minutes over. So here is really what I want. I take my generator, I apply the function f to points in its support. I look at that expectation. Now, if I sample these things uniformly, I know that I'm going to get product of expectations, right? Now, I just want that these expectations should be close to each other. I'm not asking you to get the distribution right. When we were doing this over 0, 1, there was no difference. When you're doing it in the unit complex plane, there is a huge difference, right? Like just think of all the ways you can get expectation 0 in the unit complex plane. There's a lot of ways to do it. But this is the right definition that we want to be working with. Okay. Why would you want to do something like this? Well, sorry about that. So firstly, this is a class of functions you need to fool in order to fool, if you're going to fool all of RL, right? These things can be computed using fairly small width branching programs, and this, it's not very surprising. What you do is just think of each of these colors as some let's just say they actually have norm 1. So just think of it as exponential I times theta j. So the final function is just the sum of these theta j's, right? So basically you compute the logarithms. You just keep track of the summation of theta j to sufficiently many bits in precision. You're not getting it exactly right, but we only care about fooling expectations, so it's fine, right? So in order to fool all of RL, you need to handle these things first. Okay, so why did we pick on some weird class in RL that nobody ever studied before? Well, it turns out that these things are, it's not surprising. This is just the Fourier transform going on, and they capture a lot of things that we've talked about. For example, the first obvious example is modular tests, right? Where I take my bits x1 through xn, and I compute out some sum, like summation ai xi modulo m, and then I decide that some congruence classes I'll accept, others I'll reject, okay? We didn't know how to fool these things once m becomes like polynomially large in n. There was a lot of work just doing the composite case, and so on and so forth, even for small moduli. It's very easy to encode these as a Fourier shape. You'll just take functions which map to the complex roots of unity, right? Standard trick. Okay. Obviously, these things generalize combinatorial rectangles where you just have two values, 0 and 1. In fact, they fool much more than combinatorial rectangles. The reason why they're called Fourier shapes is that they generalize this other class called combinatorial shapes, which again most of you have never heard of. It's very simple. It's very similar to combinatorial rectangles. In combinatorial rectangles, you want the sum of the fj's to be n. You want them to all evaluate to 1. In combinatorial shapes, you get to look at the sum and then apply some arbitrary function to it, right? So Fourier shapes, they generalize this notion also. And the thing they do, the reason we actually came up with this was because they also fool half spaces. What are half spaces? They are functions of the form summation wj xj minus theta, the sign. And this is a class which has attracted a lot of attention, maybe undue attention in the last 10 years or so, starting with this work of Rabbani and Shpilka. Very first work, they gave hitting set generators for these with inverse polynomial error. This was followed by this work that I did with Elias and a bunch of others, which gave a pseudo-random generator for these things, proving just that bounded independence suffices to fool them. Now, it's not even clear that these things are in RL, but Mecca and Zuckerman, among other things, they proved that actually these are very good approximations in RL. So in order to de-randomize all of RL, you've got to de-randomize half spaces, right? And a lot of these previous works, at least on the PRG side, what this basic hammer there was the central limit theorem. You take a half space, you say, okay, I know the distribution is going to look like a Gaussian. The problem is it's not quite a Gaussian, right? It's a discrete distribution. So already when you compare it to the Gaussian, you have some error, like 1 over root n error. And it's not clear that this approach will ever lead to generators which give you inverse polynomially small error. So we are doing something very different. I'm pulling one of those tricks where when we wrote this paper, we said we use the central limit theorem, and now I'm telling you we don't use the central limit theorem. But yeah. Okay, so fooling half spaces is actually this very natural thing. You have a weighted sum of variables x1 through xn. You really want to fool the CDF of this thing, right? Because I could place my theta anywhere, so I really want to fool this in CDF. And it turns out that to do this, it suffices to fool the Fourier transform of this random variable, summation wi xi. So what is the Fourier transform of this random variable? It's defined for all alpha in the range 0. Oh, I'm assuming here that the wi's are integers, which you can do without loss of generality. So now what is the Fourier transform going to look like? You just take all alphas in the range 0 to 2 pi. The Fourier transform at alpha is given by this exponential sum, which decomposes nicely into a product of alpha j's xj's, right? And this is actually where we are using the full power of our definition, because in all the previous cases, the map was really nice. It was either to the complex roots of unity or 0 or 1 or something. Here you have to really deal with all kinds of alphas. And basically the alpha goes and multiplies the w. Who knows what point you get, right? So this is where the full generality of fooling Fourier shapes is useful. Okay. Now hopefully I've convinced you that there's some reason to try and fool these things. Now let me tell you, so we give a generator for these with seed length, which is essentially logarithmic in all the important parameters. There's some log term, as usual, hiding around there. This covers a lot of these things which I'd call natural statistical tests in log space. Like a while back, Yishai was asking about things like, if I hash balls into bins, I want to get the entire distribution right. Can I do that? This will actually do such things for you. Right? So it's not just tail bounds, it gets the whole distribution correct. But it's important to point out that there are things that this doesn't cover, like read one CNFs in particular. I don't see that this generator directly works for read one CNFs, right? Because everything which is a Fourier shape is going to be a small width branching program regardless of the ordering of the input variables, right? And we kind of use this property fairly often in the generator construction. So it seems like this is going to cover a lot of natural tests. In fact, I'm hard pressed to think of natural tests that it doesn't cover, but certainly things that are only small bits for certain ordering of the bits, it's not going to cover for you. Okay, so again, as you can imagine, given everything that's come before, variance plays a big role in this generator also, right? Okay, so we're dealing with random variables which are taking values in the unit complex plane. Let me see if I have a picture here, right? So, okay, it takes values all over the unit complex disk, and then you have the mean, which is just the center of gravity of these points. You have the variance, which is the expected squared deviation from the mean. Now, a fairly intuitive statement is that these things cannot be high at the same time, right? Because really, in order to have large mean, what that means is that your random variable needs to be concentrated somewhere near the edge of the disk. And if it's concentrated there, you're not seeing a lot of variance. Conversely, if it's all over the place, it's very strange to expect the center of gravity to be off somewhere at the top of, towards the boundary of the disk, right? So this is, you can actually prove this statement. It's something which you're very familiar with in the plus minus 1 case, and it as the sum of the variance and the mean squared is at most 1. Okay. So why is this interesting? Well, very directly now, the total variance comes into the picture. If you just say, I have a Fourier shape, what is its expectation, right? Because under the uniform distribution, the expectation is the product of individual expectations, and each expectation is bounded by something like the square root of 1 minus sigma squared. So basically, a small calculation tells you that the expectation is exponentially small in the total variance. Okay? So when the total variance across these things is high, then basically things mix, and essentially the most of the time you're very close to 0 in expectation. Okay. So high variance shapes have expectation close to 0. And this kind of makes them easy to deal with. Okay, so this is the third talk. It's very close to lunch. I'm not going to get into the details here. But what you can basically do, if there's high variance, you don't need to be very careful about getting the distribution right. You just kind of hash into buckets. In each bucket, you make sure you get some constant error, and then you kind of just amplify it. If you've seen the Nauer and Nauer construction, right, the Nauer and Nauer paper on epsilon bias sets, there's one construction there, the most tedious construction of all, which makes this distinction between light and heavy parities, right? Where they say, okay, heavy parities, you can do whatever you want, it's going to work. It's only the light parities where it depends on very few variables that you need to be careful about. It's the same thing here. You can think of light parities as having low variance, heavy parities as having high variance. Okay. So really the crux of the matter is the low variance case. One of the things we do to handle the low variance case is to prove a generalization of this lemma which we had to variables in the complex plane. Again, you have this notion of total variance, and we say that if things have small total variance, then even k-wise independence will give you a good estimate of the expectation of the product. But this is really only a small part of what's going on here. At some level, I think the contribution here is the definition of the class, because it has all these nice composition properties, as we'll see. Okay. Let's now focus on the low variance case. Let's assume that if the variance is high, that case is easy. Okay. Now, in all of these examples I gave you of things we were trying to fool, if we forget about combinatorial rectangles, for things like half spaces, the alphabet is just 0, 1, right? So why are we defining shapes where the alphabet can be of size m? Okay. So let me tell you why we do that. Let's start off with a Fourier shape where the alphabet is only of size 2. So you get one complex number for this point, one complex number for that point. You multiply these things together. Okay. Okay. We're trying to come up with a pseudorandom generator for it, right? In rectangles, the first thing we did was to reduce the alphabet from m to root m. Here, we're already at alphabet 2. I don't see, there's not much scope for reducing the alphabet any further, right? So let's try instead and reduce the dimension. But we want to reduce the dimension down to root n because we want our recursion to end in log n steps, right? Okay. So what we're going to do is to hash these various bins into, so sorry, I called these things bins. I'm going to hash these into root n groups. Okay, I'm going to group them, make root n groups, each of size roughly root n each. Okay. Now what's going to happen within each bucket is that I really have a Fourier shape of dimension root n. Okay. Let's say I know how to solve the problem in root n dimensions. So I'm trying to do a recursion here, right? So I've I have these root n buckets. Each of them contains a Fourier shape of dimension root n. If I had a PRG for root n dimensional shapes, I could apply it here. What would that PRG give me? I claim that it's going to take each of these things, okay, and make it into one Fourier shape over a larger alphabet. Why is that? Okay, let me focus on this one. I have a generator for root n dimensional shapes. I plug in a seed, and then, you know, I figure out what values I want to assign here. Each of them gives me a complex number. I multiply that back. Finally, what happened is, for this value of the seed, I got a complex number. Okay, next seed, next complex number, next seed, next complex number, and so on. In essence, this generator took root n Fourier shapes. So it took these root n coordinates, okay, and it compressed them into one coordinate, but it blew up the alphabet size. The alphabet size became 2 to the r, where r is the seed length for the PRG for root n dimensional shapes. Okay. And now I have these root n buckets, right? I clearly don't want to use independent seeds across all these things. So in the very first example we saw of balls and bins, we just used the same seed, we did a union bound. The next example, we kind of just use k-wise independence across the seeds. And now here you need to do something, you know, a little bit cleverer. What is the property we want from these different seeds, right? So I claim that what we are trying to do with these various seeds is to just fool another Fourier shape now in root n dimensions and over a large alphabet. Because if I was really using independent seeds, right? So basically I have an alphabet of size 2 to the r, I get a complex value. I do that independently here, I get a complex value. I do it independently here, I get a complex value. This is the thing I'm trying to de-randomize. And this is exactly the problem of de-randomizing one Fourier shape in root n dimensions over an alphabet of size 2 to the r, right? So with these two steps, I actually managed to bring the dimension down to root n, but I've paid for it by blowing up the alphabet to something 2 to the r. If the seed length is logarithmic, then this is just some large polynomial. So now what we do is we just do this sampling trick to reduce the alphabet within each bucket. You know, so we have a large alphabet here. Day one, we'll sample square root, bring it down to square root. The next day, bring it down to square root again, and so on and so forth. And you keep hitting it with this lemma which says that, you know, if you're doing things, low variance things, limited independence suffices to fool them. Okay. So basically, you get a generator. So at a high level, what's going on? Even if I start with an alphabet of size 2 in n dimensions, the first step is I hash it into root n buckets. For each bucket, I will use a generator for alphabet size 2 and dimension root n. Across the different buckets, I recycle the seeds, and that recycling is done using a pseudorandom generator for Fourier shapes in root n dimensions over a large alphabet. Okay. It's kind of late in the day, so maybe this is not making a whole lot of sense, but the high-level idea is that these things have some very nice composition properties, which makes it so overall you do this, and you get a seed length, which is something like log times log log n squared. So I just want to point out that the main technical lemma here is this generalization of what I showed you before. The proof, though, is far more analytic. You know, I can't say I really understand it. It would be nice if there was some algebraic interpretation of this statement in terms of some roots of polynomials. Okay, so I guess let's get an early lunch. Sorry.
The whole structure looks like top-down view of Nissan's generator in some sense on this model.
Well, I don't know, right? So this Nissan kind of recurses by going from n to n over 2. You were trying very hard.
No, this goes from n to slope. No.
Yeah. But in what sense do you feel it's similar? I agree. So okay, so we seem to have this, nice new technique and some, we've learned some basic facts about when limited independence can fool things like products of random variables, but we've still not managed to improve the log squared and bound from, 20 years back, which is kind of unfortunate. At least at this point, I would say that, it's becoming increasingly harder for me to come up with tests in RL, all these things which are a lot of these natural tests in RL, you compute some linear form on the inputs. They are fairly order independent, so it seems like, maybe this generator or some version of it could work. But we still don't know a better generator, even just for width-3 branching programs, right? And we do have hitting set generators for that. We don't know PRG. And again, this generator, it would be really nice if it fools more on the AC0 side of things, right? So here, on the RL side of things, the barrier here seems to be going to these tests, which are only in RL for a specific ordering of bits. In this generator, we're doing all these things like hashing things into buckets and hoping that it's just some reasonable class and so on. All of that will break down once you deal with these things where the order is very important. On the AC0 side, it would be very nice if this generator did anything which is not read once, right? All our machinery is geared towards saying, if I have a product of independent random variables, how do I de-randomize that? Well, if your DNF or CNF is not read once, then this independent structure breaks down. But maybe there's a completely different analysis which does work for the non-read ones. Ishai?
Can you handle read 2?
No. Read once, just read. Well, I don't know, read 2. No, I don't see it, really, no. Yeah, so if you want to think just about the lower bound question, as I said, it takes a bit, what did our generator do, right? So we said, let's take half the bits, let's set them epsilon biased, and now if the other bits were truly set uniformly, then, actually the expectation would not change. And then you de-randomize the uniform part, right? So then you say, okay, I'm not actually going to set them uniformly. I'll set them, half of them epsilon biased. You go on recursing. So it seems like if there is a hard function underlying this construction, it ought to be something like this, which I mentioned before. You take a small bias set, take balls of a reasonable radius around it, and maybe this is a hard function for depth 3 AC0. And lastly, one thing which would be really nice, and I haven't, like the others, I have no clue whether it's something like this. A lot of times when you use independence, it's really to compute expectations of products. The fact that in some situations at least you can do it without true independence, it seems like something which could be broadly useful outside the context of pseudorandomness. All right, so thank you all for your patience, and I'll stop right here.